Hi, welcome everybody. My talk today is about one very specific area about formal test benches, and the focus again, like the previous talks, is sign off, because the goal with formal is again sign off, meaning that I have to finish what I promised to do and I have to have metrics in place, and maybe somebody's relying on that, so I cannot not finish and just find bugs. But the area I'm going to talk about is end-to-end checkers. Jin mentioned that as part of the formal test bench. One question to those of you who haven't seen some of the next slides before is that what is inside the end-to-end checkers? And again, going back to simulation, it's actually fundamentally no different than what's inside the end-to-end checkers for simulation. If somebody gave me this memory controller to verify with simulation, how will I verify it? I'll build a scoreboard, and the scoreboard will detect, well, what is my design supposed to do? I'll try to understand that. My design is supposed to do read after write combining. If I had a previous write sitting in my memory, in my store queues, and then I do a read after that, I have to do combining of that. I don't want to send that transaction to DDR2. I want to split some transactions in some cases. I want to, if my address is out of space, I want to give an error response to the EXI interface. All of that knowledge is built inside the reference model, just like you would build in a simulation-based reference model. The only difference is that the reference model has to be formal friendly, and we'll talk about some of that today. And you cannot, you can almost never take the existing reference model built for simulation and reuse in formal. That almost never works. But you can take the knowledge about what's in the reference model and build it again for formal. And if you build it for formal, you can reuse in simulation. That works, but the other way doesn't work. And then, if I'm doing end-to-end verification, most of the code is actually in the reference model, but there is also some amount of code in SVA. You can restrict yourself to writing simple SVA, or you can write more complex exotic SVA. But I don't know any interesting design where you can write the entire reference model in SVA itself. So that I think is beyond anything, the capacity of any reasonable syntax or semantics associated with the SVA language. So what we'll focus on, the keyword here is efficient. And I want to just talk about very simple concepts here for people who haven't seen formal before. And talk about two specific things, and how to make the checkers more efficient. And if you haven't seen formal before, just used to simulation, then there's some cool things here. Well, again, like I said before, tools run into complexity barrier, and again, it's not a tool problem. It's not a problem specific to your tool. You can take any other tool. You'll most probably still have the same quote-unquote problem. To me, it's not a problem because I know it's a theoretical problem with the capacity of state space search, but I know I can solve the problem by changing the problem. And that's what these meetings are about. So let's talk about two concepts, symbolic variables. And actually, it may sound like a fancy name, but any of you who has dealt with configuration registers, the concept is very similar. So the idea, I have a memory controller inside, the guts of the memory controller inside in this picture here. And I have a register block here at the top, which I can write to from an external APB bus, and I can change the configuration settings for my register. And the kind of registers it has are, for example, things like config policy, which is dictating the policy being used by the arbiter. And for different versions of the memory controller, or maybe for the same memory controller in the field, I may want to change the arbitration policy. But the well-known way of operating these designs is that I don't want to change the configuration while the design is in operation. So after reset, I'll first set the configuration. Then the design will do all the normal operation. And then if I ever want to reset the configuration, I'll let the design become idle, then reset the configuration. And that's a very common assumption that the simulation guys make day in, day out in their verification. And why wouldn't I make the same assumption if the design team doesn't care about any bugs in the design while the configuration register is changing at the same time as operation? So I don't want to make it more difficult than what people care about. So now that means that configuration register, for example, specifically this signal called config policy, has to be the same value in any given counter example that I give you with formal, or at least while traffic is going through the design. And what I can do is I can add cut points in my design running with formal. Tell the formal tool, well, ignore the configuration register logic. If you're worried about bugs in the register file itself, then verify it separately. Do verify it, but verify it separately. You can verify it separately both with formal and simulation. But let's say right now you're worried about verifying the rest of the design. So cut point on those signals and make them stable. And that's a concept which many of you may have used before when you're doing formal. And making it stable is telling the formal tool that I want to verify different values for these signals, but in any given trace of a formal run, I want that value to be fixed and fixed to the same value. Now, as you will see later, in one formal run, the tool is actually verifying many, many different traces. But in any given trace, the value for config policy will be the same. And that actually makes it easier for the formal tool to run, because some weird state space of the design, which is exposed when the registers is changing at the same time as the design, things are going on in the design, that doesn't get exposed to the tool unnecessarily. And the way I implement that is with another SVA property. It looks as simple as this. And basically just focus on the property line, which is just saying that the config policy value is the same as the config policy value in the previous cycle. And because this assertion is true on every cycle, it's always true. So I'm going to assume this property, and I'm going to assume this property forever. Now, it doesn't mean that the config R policy has a fixed value. It just means it has the same value in any trace. But the formal tool is going to verify all possible traces. In different traces, it will have different values. So, I mean, what the tool is going to do is going to, for every input I choose to make stable, in each trace, the value of the variable is constant. But across different traces, in a single formal run, the values could be different. And the example that we talked about before is the configuration registers. But also, what I'm going to talk about now is symbolic variables, which is new variables I will introduce to make my checkers more efficient. So I'm going to switch topics and talk about a different class of techniques. And this is just splits is the word I'm using today. And I'm going to be talking about to split or not to split. And so I'm talking about different splits. There is many, many different ways in which you can split the problem that you're verifying. But remember, the back of my mind, what is in my back of mind? It's complexity. It's trying to understand what is going to be hard for the formal tool, where it's going to explore the state space, where it's going to hit the exponential wall, and keeping that in mind from the beginning of the project. One of the very simple things I can do is that, I have a property like the following here. And this is just the property part of it. On the left-hand side, I have A and B. On the right-hand side, I'm comparing C to D, and there is another variable E. And A, B, C, D, and E can all come from either the design or the reference model, doesn't matter. So they both have a cone of, all of them have a cone of influence. And if you think about different kinds of design, C equals D could relate to, I'm actually trying to verify the data is correct. The data from the design equals the data from the reference model, for example. And E could be some control property. So if the data comes out, then something else will happen. The length has to be correct, for example, or something like that. It has to be consistent. But the thing about this is that the same property can be easily, syntactically, without even thinking anything about it, split two different ways. A and B implies C or equals D, that's one way, and A and B implies E. And you're verifying exactly the same, effectively verifying the same thing. And the sum of those two proofs is actually less than the sum of the original proof. The runtime you won. And you'll win a lot of times because if the cone of logic is disjoint, and I've given a very simple example here, and some tools may actually be doing this automatically under the hood, and you may not even need to do that. But it can get more complex, when this AND is actually buried inside other code and all that. But if you're able to split the property itself into multiple ways, and those multiple ways are equivalent to the original property, and if that simplifies the cone of logic the tool has to look at, then you win. Or you can lose also. You can lose if you split it two different ways. It was taking me 24 hours to run earlier. I split it two different ways. Each one of the runs still takes me 24 hours. So now I have to spend 48 hours. So and that's another thing you have to think about or worry about. So the benchmarking that you have to do internally, one of the things we do in almost every project is we plot the runtime and we watch the curve a lot, and we try to understand where the knee of the exponential curve is. And for us as a company, all four of these slabs in the pyramid are useful, extremely useful. And the biggest value we add as a service company is only at the top of the pyramid. But if you're going to use formal only 10% of your time or 25% of the time, I would say don't even try to do this. And if you want to try to do this, do it, because I'm sure anybody in this room can learn. But then do give 100% of your time doing that, and block off like 1 year or 6 months or 3 months or whatever you have. And then you can learn a lot and you can grow a lot in that role.